Maybe we can start now. So, welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's first speaker is Dr. Suratna Das from Ashoka University, and she's going to talk about some background checks for worm inflation.
Well, thanks, Anish. Thanks for inviting me to give this talk. So today I have decided to talk on a paper which I wrote with Rudni Ramos in 2021. I chose this paper. As you can see that this paper is a little old already, but I chose this paper because this is probably the easiest paper I have ever written, and it's very easy to convey the physics in a small talk. So, uh, so as you can see that the key word in this talk would be worm inflation. So let me start with first of all, what inflation is. Okay, so as you can see that this is pictorially how our universe has evolved since the Big Bang. So this is the initial time when, as we think that the universe started evolving from a singularity, and since then our universe is expanding. And at the very beginning, when the age of the universe was nearly 10 to the power minus 35 seconds, the universe had gone through a very rapid expansion for a very brief period of time, and we call this period inflation. Okay, so during this time, not only the universe was expanding, the expansion rate was almost exponential. So it was expanding with an accelerating rate, which was very contrary to the rest of the evolution through which our universe had gone through at later stages. So one inflation ends, the universe enters what we call as a radiation dominated era. We call it radiation dominated era because, as you can see, the universe started with a very hot and dense uh, state. And as because the temperature of the universe was very hot at the initial time, on the particles during that time were highly relativistic in nature. And that's why we can treat these particles in the relativistic regime. So we call this regime as radiation dominated era. And as the universe keeps on expanding, the temperature keeps on falling down. And at some point of time, the temperature of the universe falls so much that now the particles will become non-relativistic. And when the particles can be treated in their non-relativistic regime, we generally call that the universe had entered a matter-dominated era. Okay, and a very important thing happened during this matter-dominated era is the decoupling of these cosmic photons from the rest of the cosmic plasma. So what happened at this moment is that, as we know that photons interact with rest of the matter electromagnetically. So as long as there are electromagnetic charges available in the cosmic plasma, the photons will keep on interacting with the cosmic plasma. But what happened when the age of the universe was nearly 380,000 years, the temperature of the universe fall below the binding energy of the hydrogen, which is 13.6 electron volts. And when that you, I mean, as you can see that when the temperature of the universe fall below 13.6 electron volts, a proton and an electron can come together and bind together to form a neutral hydrogen. Okay, and the photon in the cosmic path will not have enough energy because the temperature is now below 13.6 electron volts. So the average temperature of the photons are below 13.6 electron volts. So these photons cannot knock this electron off from this stable hydrogen atom, and a stable hydrogen atom could form. Once these hydrogen atoms form, there were very less electromagnetic charges left in the cosmic plasma for the photons to interact with. And then, as because there are no electromagnetic charges left in the cosmic plasma, the photons got decoupled from the rest of the cosmic path. And then, since then, they remain decoupled. And today, we are observing these photons in this microwave range. So we call this bath of photon that we observe today, which originated long back in the evolutionary history of our universe, as cosmic microwave background. And this cosmic microwave background is very important because whatever happened before the formation of this CMBR can leave their imprints on the CMB photons. So basically, why we need the CMB photons for this stuff is that because inflation happened long before the CMBR was formed, inflation can in principle leave their imprints on the CMBR, and they do leave their imprints on CMBR. So when we measure the different features of cosmic photons, we can infer what had happened so long before in the evolutionary history of the universe. So the discovery of CMBR was very important for the cosmology and cosmology became science once CMBR was discovered. And CMBR was discovered actually by accident in 1965 by two astronomers, Penzias and Wilson. And then they received the Nobel Prize in 1978 for this discovery. What they have seen is that there was a very uniform temperature of these cosmic photons all over the sky of almost of the range of 3 Kelvin, and they couldn't see any fluctuations in that CMB back then. But in 1992, there was another satellite launched, which was named Kobe. Kobe could see that the CMB photons not only has a very uniform temperature, but it has slight fluctuations of the order of 10 raised to power minus 5. So in the microkelvin range. And these fluctuations got a better measurement by WMAP in 2003, and Kobe got the Nobel Prize for confirmation by confirming this observation of CMB fluctuations in 2006. Okay, so CMB photon not only has a very uniform temperature of 3 Kelvin, 2.73 Kelvin all across the sky, but it has tiny fluctuations. These red dots are the hotter dot. This red band is actually our galaxy plane. But later on, as you can see in this picture, so this is what Kobe had seen. This is the sky. So this is the resolution of Kobe. This is the resolution of WMAP. And today we have even better resolution by Planck observation. And you can see how nicely Planck has mapped the CMB sky, how accurately it has mapped the CMB sky. It has these red dots are the hotter regions, these blue dots are the cold regions in the CMB sky. Okay. So we actually now have measured this CMB sky very nicely. And why it is important? Oh, sorry, no, before going to that, we also know that the CMB photons have not only, they have fluctuations, they are also polarized. And there are two kinds of polarization modes. One is E mode and the other is the B mode. This E mode and B mode can be differentiated by looking at the patterns. So the E modes are mirror symmetric and the B modes are antisymmetric when you look at its mirror reflections. Okay, so this is how you differentiate between E mode and B mode in the sky. So CMB photons are also polarized, and what we have seen is this, that so if you look at this first picture, this is the background photon which fits a very nice black body spectrum of 2.73 Kelvin. This is probably the finest black body spectrum ever seen in nature. And you can see these small dots. These are the actual error bars on this observation. So how accurately it fits a black body spectrum. So that means a black body spectrum means these photons were actually in very tight thermal coupling with the cosmic plasma before it got decoupled. Okay. And the second picture are the 2-point correlations of the CMB fluctuations, the fluctuations of 10 raised to power minus 5 order, which was first seen by Kobe. Okay, and this is a data by Planck, This is the latest data. And what we measure is the correlation between the temperature fluctuations on the sky. Okay, that correlation means if what are the statistical correlation between a temperature on this part of the sky and that part of the sky. Okay, and so we are looking at two different parts of the sky, and we are determining the 2-point correlation functions of these fluctuations. And that's because we are seeing mapping these fluctuations on a spherical sky. It is actually mapped with this L is the spherical harmonics, and so this is actually plotted as a function of spherical harmonics, and these small blue dots are basically the observed plots observations with error bars. Okay, so you can see again not only the background temperature of the CMB photons, but the fluctuations also are very accurately measured at today's state. And this red dot, a red curve, which has fitted the data so nicely, is actually a theoretical prediction from inflation. So inflation, so this is the success story of inflation, that it predicted this spectrum, and this has been seen. So this was predicted in 1980s, and as you can see, this CMB fluctuations were discovered in 1990s, and this uh, plot, this prediction from inflation actually fits the CMB data so well. Okay. And if you can see, if you also want to plot the polarizations of the CMB photons, so this curve is the temperature fluctuations that I have shown in the second plot. And if you want to plot the polarizations, so polarizations are order of magnitude smaller than the temperature fluctuations. So this theta is actually basically temperature E mode cross correlation power spectrum. This E is the E mode correlation function, and this B is the B mode correlation function. Okay, and this B mode correlation function has a very important aspect as long as inflation is concerned, because this BB mode, once it is detected, this has not been seen yet. Okay, this has not been detected yet in the CMP spectrum, but once it will be detected, one can directly measure at what scale the inflation has taken place. We still do not know the exact scale at which inflation has taken place. So this BB, people are now waiting for this BB spectrum to get detected, and yes, it's going to play a very major role in ruling out many of the inflationary models. Okay, so let's talk about inflation. Okay, so of course, the evolutionary history of the universe is governed by Einstein's general theory of relativity. And as I said, the inflation is a very brief epoch at the beginning of the universe, when the universe had expanded exponentially. So, and the dynamics is governed by Einstein's general theory of relativity. So, these are the Einstein field equations. So, what Einstein field equation tells us, on the left hand side, we have this tensor G mu nu, which tells us how the background geometry evolves. And on the right hand side, we have this T mu nu, which is called the energy momentum tensor, which tells us how the matter in the universe evolves. So, what basically this whole equation tells us is that the evolution of the geometry, which is on the left hand side, is coupled with the evolution of the matter in the universe. So the evolution of the matter affects the evolution of the background, and the evolution of the background affects the evolution of the matter. So these two evolutions are basically coupled. Okay. So what is the background geometry for the universe? It is the Friedman-Robertson-Walker. Well, sometimes I would also like to plug it in the name of Lemaitre. So I would like to call it FLRW metric rather than FRW metric. But anyway, this is how the background metric of the universe looks like. It's mostly almost like a Minkowski metric, except there is a factor A sitting here. It is a time dependent factor, and it tells that the spatial part of this metric is time dependent. That means it can expand or it can contract. But by observationally, we know that the universe is expanding. So this is a monotonic function of time, and it will say that the universe is expanding and the spatial part of the universe is expanding with time. Okay. And this factor, which is sitting, time dependent factor, which is sitting in front of the spatial part of the metric, is called the scale factor. And during inflation, as I said, it is almost an exponential factor. Thus the scale factor looks like exponential of ht, where h is the Hubble parameter. Okay. So this is the geometry. And what is the matter in the universe during uh, inflation? So we now need to drive the universe to expand almost exponentially. It cannot be done by any standard matter. Okay. We need a very exotic kind of a matter, such as we need a scalar field which is slowly rolling down its potential. What do I mean by slowly rolling down? I mean that the kinetic energy of the scalar field is much smaller than its potential energy. To achieve that, we need to have a very flat potential so that the kinetic energy is very small. And the flatness of this potential is determined by the slow roll parameters, which I have written here. As you can see, epsilon v is the first slow roll parameter, which is proportional to the first derivative of the potential. And the second slow roll parameter is given by this eta v, which is the second derivative of this potential. And both these parameters remain much smaller than 1 when inflation takes place. Okay. So this ensures that the potential can remain really flat, potential should remain really flat, so that the inflaton can slowly roll over this flat portion of the universe and can drive the universe to expand exponentially. I'll come back to this point at a later stage. It has a important discussion in our today's talk. But as you can see, when the potential becomes quite steep, inflation ends. So when these slow roll parameters become of the order of 1, or when the potential becomes quite steep, inflation ends. Okay, so this is the story of inflation. The other important point is this period after inflation ends, which is called the reheating phase. So as I said that during inflation, the universe had expanded exponentially. And as universe expanded exponentially, whatever matter was there before the inflation had started, everything will dilute away exponentially. So when inflation ends, basically we will have a universe devoid of everything. It will be a very, very cold universe where there is nothing. So you need to create the radiation so that the universe can enter a radiation domination era once inflation ends. So basically you have to reheat the universe. For reheating the universe, you basically need such a shallow or a bottom of the potential where the inflaton can oscillate and can decay to other particles. Okay. So for basically, so this is the standard picture of inflation, where you need such a very stringent form of a potential, where first of all you need a very flat portion, and then you need these bottom of this potential, so that first of all you need a flat region so that inflation can take place, and then this bottom of this potential, so that at the end of the inflation the universe can reheat again so that it can enter a more regular radiation domination era. So please keep this picture in mind. We'll come back to it at a later stage. Okay. And as because this inflaton field has quantum fluctuation, so this is the background field which slow rolls, and which is a time dependent part of it. And then there are quantum fluctuations. As because there are fluctuations, and I said during my previous slide here that my geometry is actually coupled with my matter. So if the matter has a fluctuations, my geometry will also have fluctuations, background geometry, right? So if I go back, then these fluctuations in the inflaton field will induce fluctuations in the geometry, and so it will induce fluctuations in G mu nu, and G mu nu is now a tensor. Okay, so once you fluctuate a tensor, it will create all sorts of background fluctuations like scalar, vector, and tensor. This tensor modes will generate that BB spectrum that we are still looking, we are still waiting for it to be discovered, and that will give you the scale of inflation. And these scalar fluctuations actually give you the CMB fluctuations that we observe today. Okay, that is how inflation leaves its imprint on the geometry. Okay, but we are not going to talk about the perturbation at all in today's talk. What we are interested in is to talk about this background dynamics of inflation. Okay. Today's topic is how inflation ends, which was a problem which people has initially faced when people were talking about inflation, and they gave it a name called graceful exit. So universe should gracefully exit from this inflationary phase. Gracefully exit means it should go to a radiation dominated era very smoothly. But as I had said that you need to go through a reheating phase so that inflation first can stop and then it will go to a reheating phase and it can enter a radiation dominated era. Okay. So inflation, of course, is a phase again when the universe has expanded exponentially during a very brief period of time. So what do I mean by this accelerated expansion? So if you look at if you feed in the FRW metric in the Einstein field equation with matter, and in cosmology, we always treat matter as perfect fluid. Perfect fluid means you can relate the pressure of the perfect fluid with its energy density with this simple relation. So P is equal to omega rho. Omega is called the state parameter of that perfect fluid. So if you feed in your FRW metric in Einstein, so this FRW metric is on the left hand side, which will determine the evolution of the universe, of the background geometry. And this matter is the matter in the right hand side for this T mu nu that I had shown before. And then we'll get two Friedman equations, which will tell us about the expansion history of the universe. So this is the first Friedman equation. This is the second Friedman equation. Look at the first Friedman equation. It is A dot by A. So A dot is the rate at which the universe is expanding. Okay. So AT is the scale factor, and this is the rate at which it's expanding. And A double dot will give you the acceleration, right? So if A double dot is, in general, A double dot is less than 0 for normal matter. That means the universe is expanding, but with a decelerating rate. But if A double dot is greater than 0, only then we will get an accelerated universe or accelerated expanding universe. But to achieve A double dot to be greater than 0, you can see that now we need a perfect fluid with a state parameter. Omega should be less than minus 1/3. Only then A double dot will become positive. Okay. Well, we know that such kind of we actually know one kind of perfect fluid which has such a state parameter, which is a cosmological constant, which has a state parameter of omega equal to -1. But the problem with cosmological constant is that you can drive inflation, but you cannot end it. Okay, so there is no graceful exit. So cosmological constant, though it can drive inflation, is not a good candidate for being an inflaton field, because once you have cosmological constant, you cannot basically end inflation. It will basically drive a de Sitter kind of universe, and you cannot end inflation. Well, so what do we need? As I said, for that we need an inflaton, and it's slow roll. It should slow roll. So look at the energy density and pressure for a standard scalar field in an expanding universe. So you can see the scale factor is sitting here. Okay. And let's say that if the energy density and pressure is dominated by the kinetic energy, then you will have a perfect fluid for which the state parameter would be equal to 1. So if the scalar field is kinetic energy dominated, then you cannot have inflation. Okay. However, if it is dominated by this gradient term, then you will have a state parameter of minus 1/3, but you need a perfect fluid of state parameter omega less than minus 1/3. So this is also not enough to drive the universe to accelerate. Okay. So you cannot have a kinetic energy dominated scalar field. You cannot have a gradient energy dominated scalar field. But if it is potential energy dominated, as you can see, now the state parameter has become minus 1. So potential energy dominated scalar field, which we call the inflaton field, can drive inflation. Okay. So the potential needs to be very flat, as I had already said, so that the kinetic term should be negligible, and slow roll of inflaton on its flat potential can take place. And slow roll parameter epsilon v should remain much smaller than 1. So this is how inflation can take place. Okay. And if you look at the inflaton equation of motion, so this is an approximated Klein-Gordon equation. So I have neglected the kinetic term, which was phi double dot sitting in front of it. So this is the slow roll approximated equation of motion of the inflaton field. And if you have an inflaton field where the kinetic energy is much smaller than its potential energy, then you can show that epsilon v, and including this equation of motion, epsilon v will remain much smaller than 1. And how to end inflation? So to end inflation, you have to start with a epsilon which is much smaller than 1, then the epsilon should slowly grow and become 1. Okay, only then inflation can stop. So what you need basically is an epsilon which will start as much smaller than 1, and eventually it should grow and become 1, and then the inflation will end. I have plotted this evolution as a function of number of e-folds. So number of e-folds is a way of keeping time during an exponential expansion. So this is keeping time in exponential order. Okay. So nothing very exotic about it. It's just measuring time in exponential order. Okay. So basically you need a potential for which your epsilon v should be a growing function of time. Okay, so d epsilon v dn should be greater than 1. This is the standard picture. So basically your epsilon v is much smaller than 1 when the potential is flat, and when the potential becomes steep, your your epsilon will start to grow, and at some point of time it will become 1. So at this point, you can see this is phi n, that means this is the end of inflation. So at this point, your epsilon v will become 1. So this is this point. Okay. This is the most standard picture. But we are going to talk about a variant inflationary scenario, which is known as the warm inflation. Okay. What is warm inflation? So warm inflation is, rather than having a reheating phase at the end of inflation, people started asking why not to have reheating during inflation. That means the inflaton field will be coupled to a radiation path, and the inflaton field will keep on dissipating its energy to the radiation path. Okay. So if you have a radiation bath at the beginning of the inflation and there is nothing which is feeding to the radiation bath, the radiation bath will exponentially decay away. But as because now in warm inflation, this inflaton field is coupled to the radiation bath, it will keep on feeding its energy to the radiation bath, and one can show that one can actually maintain a constant radiation bath by this mechanism. And the good part is that when inflation ends, as because there is already a radiation bath existing, it will smoothly transit to a radiation dominated era. So one will not require such a shallow, deep end. This very stringent form of the inflaton potential is not required in warm inflation. one can have a variety of warm scalar potential which can drive warm inflation. Even this, the good part is that one doesn't even require such a flat portion to drive warm inflation. One can actually have a very steep potential. I have written papers, quite a few, at least 3, where we have shown that very steep potentials can also be sustained by warm inflation, which is not, which cannot be done in the standard inflationary picture, which now onwards I will refer to as cold inflation. Okay. So warm inflation is very different from cold inflation, and the dynamics is also very different from cold inflation, as you can see. So this is a coupled equation, and both these fluids, this inflaton fluid and the radiation fluid, they evolved as a coupled equation. So this is the difference between cold inflation and warm inflation. So why warm inflation? So warm inflation, first of all, it has quite a few very attractive features. First of all, as I said, that it doesn't require a subsequent reheating phase. Actually, till now in cold inflation, people do not know a good mechanism of reheating the universe. So this is an open problem in research in inflationary cosmology. And also we do not know about reheating phase, because the reheating phase do not leave any imprint on the CMB. So we cannot differentiate between different reheating mechanisms because there are no observational signatures. Okay. But warm inflation doesn't require such a arbitrary phase after inflation, right? It can smoothly transit to a radiation dominated phase without requiring such a reheating phase. Okay. Warm inflation can have a more enhanced scalar power spectrum, and so that it can generate a very small tensor to scalar ratio. I didn't talk about tensor to scalar ratio, but as you can see, this is another parameter. So another parameter which can rule out many of the cosmological potentials, such as lambda 5/4. As you can see in the Planck data, there is no lambda 5/4 because this is outside this plot. So basically lambda 5/4 kind of a potential is ruled out in cold inflation, but as you can see here in warm inflation, they are in tune with warm inflation. Okay. Well, there are certain other nice things. One is this that warm inflation can naturally gives you small field inflationary models, and the Planck data actually prefers small field models. So warm inflationary models are naturally small field models, so which is a good thing. And it can also significantly alleviate the eta problem and gravitino problem if you uh, take supergravity models. Warm inflation is also favored over cold inflation because of the swampland conjectures in string theory, and I had quite a few papers written on that. But I'm not going to discuss all these things, but just to showcase that warm inflation is actually has certain advantages over cold inflation. Okay. So how to gracefully exit from warm inflation? So as I said, now the warm inflation is coupled to the radiation path. So that coupling will change this inflaton dynamics. So initially it was 3H equal to minus V pi, but now there is a Q sitting here. Q is a dimensionless parameter which tells you, as because if you can see here in inflaton dynamics, there are two terms which acts like a friction term in the inflaton dynamics. One is this background expansion, which is proportional to this Hubble parameter, and the other is this dissipative coefficient. Okay, so there are two frictional terms acting in the inflaton equation of motion, and Q is basically is there a question?
No, I don't think so. Maybe
Okay.
something in the
okay. So basically Q is basically the ratio of these two uh, frictional terms which is present in the inflaton dynamics. Okay, and now you can do your slow roll calculation and can show that inflation now takes place when epsilon v is much smaller than 1 plus q, not only just 1. Okay, and ends when epsilon v is of the order of 1 plus q. So graceful, and epsilon v and q both evolves in time. Okay. Initially in cold inflation, it was only epsilon v on the left hand side which was evolving in time. Now on the right hand side in warm inflation, we have another parameter q which evolves in time. Okay. So now graceful exit will depend on both the evolution of epsilon and q. And if one can parameterize this dissipative coefficient, which depends on the temperature of the radiation path as well as on the inflaton field, and you can parameterize your dissipative coefficient like this, and you can show that this is how epsilon v and q evolves. Okay, so you can determine that from the background dynamics and the inflaton equation of motion. So how warm inflation ends? Okay, so warm inflation will end when epsilon v will become, first of all, inflation takes place when epsilon is much smaller than 1 plus q, and when epsilon v becomes 1 plus q, then warm inflation ends. And as you can see, there are so many conditions through which warm inflation can end. It just doesn't depend on only one condition that I have shown for the cold inflation. So now we have a variety of situations in which warm inflation can end. Okay. First scenario, when epsilon remains constant. If epsilon remains constant, this is a scenario where cold inflation can never end. Okay. So as I have shown you previously, epsilon should grow so that inflation can end. But as because now we have another parameter q, which is evolving in time, so first of all, you need epsilon to be much smaller than 1 plus q so that warm inflation can take place. But even if epsilon is constant, q can decrease and inflation can end. Okay. This is a scenario where cold inflation can never end, but warm inflation can end. Okay. When epsilon grows, so this is a scenario where cold inflation can also end, but warm inflation can end in three different ways. First of all, if epsilon is growing, 1 plus q can remain constant. Even though 1 plus q is not evolving, warm inflation can end. Or 1 plus q is decreasing, but epsilon is also increasing. In this scenario also, you can end warm inflation. And there is a third scenario where epsilon is increasing, but 1 plus q is increasing with a slower rate. Okay. So in this case also, you can end warm inflation. But if your epsilon is increasing and your 1 plus q is also increasing with a higher rate, in that case, warm inflation will never end. Okay. So these are the three scenarios in which you can basically end your warm inflation. Okay. And when epsilon is decreasing, if epsilon is decreasing, then also you cannot end cold inflation. So if you have a potential where your epsilon is decreasing, that is a bad potential for cold inflation. But that is not a bad potential for warm inflation. Why? Because if epsilon is decreasing and 1 plus q is also decreasing with a faster rate and can cross epsilon before q goes to 0, then also you can end warm inflation. Okay. So as you can see, there are certain potentials, that is like potentials where epsilon remains constant, or like potentials where epsilon can decrease. Those are bad potentials for cold inflations. But those potentials are not bad potentials for warm inflations, because you can choose your dissipative coefficient in such a way that you can actually gracefully exit from warm inflation. So this analysis show that warm inflation is much more powerful, and it can accommodate a variety of inflaton potentials which were initially not good potentials if you had considered the old cold inflationary picture. Okay. So these graceful exit conditions also put constraints on the combination of the inflaton potential and the form of dissipative coefficients. Okay. So this is a powerful, this is the most important aspect of our analysis, that if you now your warm inflationary dynamics is constrained by the choice of your potential and the choice of your dissipative coefficient, such as if you take a dissipative coefficient where phi is equal to c equal to 0, so there is no dependence on phi, you can show that n equal to 4 is not a good, So lambda 5/4 is not a good potential if epsilon is P is so these white regions are the regions where there won't be any graceful exit. Okay, so if your P is -2, then lambda 5/4 is not a good potential because you can never gracefully exit. Such as, and again, if there is a phi dependence, let's say C is equal to 2, then lambda 5/4 is not a good potential for P -3. Okay. So such combinations will not work because there won't be any graceful exit. So from this analysis, you can.
Hello, can I
Yes.
ask a question?
Yes, yes, sure.
Here T is temperature.
T is temperature of the radiation bar. Yes.
So is there like a heuristic way you connect temperature to say coupling, or or is there or do you really have to model it with some particle physics model explicitly?
No, no, you can basically your background, I mean, the background particle physics model will determine your epsilon. Okay. So from
Yes, I'm
particle
just
physics, you
asking
can,
about
yes.
how to constrain perturbativity in such a general case. Like, can you talk about perturbativity in such a case? If whether such epsilon has any perturbativity constraint?
The epsilon has a constraint from the stability of warm inflation. So you can do a stability analysis that puts a
Mhm.
constraint on P. P has to be less than equal to, it should be between -4 and +4. There are no other constraints.
Okay.
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 So if you study the background, the stability of the warm inflationary models, then there is a constraint on P. There are no other constraint from uh, perturbativity. You can do a perturbative analysis. So it depends on the perturbative analysis, of course, depends on the combination of your potential and the
Sure.
epsilon. And then you will see whether, I mean, but in this paper, we never discussed any perturbative thing. What we have shown that this combination is actually crucial because some of the models will never gracefully exit. Okay.
Okay. Yeah.
Then
Thank
your
you.
background dynamics will not be good enough. Okay.
Yeah.
So,
Thank you.
okay. So this is what I had to convey, that even the background analysis tells you a lot about warm inflation. Okay. So not only, you do not have to go to even your perturbative analysis, even at the background level, you can basically constrain your warm inflationary models by looking at whether they will gracefully exit or not. Okay. So, okay. Thank you. So this is what I wanted to say into this stuff.
And thank you for the nice